Welcome back. We're going to have a look at Newton's laws of motion as applied to GCSE physics. We've got a lot of objects kicking around the screen here, and in every case you can apply at least one of Newton's laws to them. So let's have a look. Newton has three laws of motion that you need to know about GCSE physics. The first law says a body will remain with a constant velocity until a resultant force acts on it. And that includes being stationary, because if you're not moving, you've got a constant velocity. So if the resultant force is equal to zero, and by resultant force we mean the sum of all the forces acting on an object. So if you are sitting right now with your weight being equaled by the normal force or the reaction force, then the resultant force is equal to zero. So if you have a weight of 500 newtons, the normal force will also be equal to 500 newtons. So in this case, there are two options for motion. If it's following Newton's first law, it must have a constant velocity or be stationary. Now, the sort of converse to this is Newton's second law, and this is where the acceleration of an object or its deceleration is proportional to the size of the resultant force. So in this case, the resultant force equals zero, or what's probably more familiar is the equation F equals ma. Now, just stating that's not enough to quote Newton's second law. But basically here, if we've got an object like a motorcycle and it's giving, the engine's giving a lot of thrust, and the drag that it's experiencing isn't nearly as much as this force here. If the drag is equal to 20 newtons and the thrust is equal to 300 newtons, the resultant force is equal to 250 newtons to the right in this case. So the resultant force is going to result in an acceleration to the left, to the right in that case. So if we're following Newton's second law, the object must be accelerating or decelerating. So those are the only four ways that anything in the universe can move: stationary, constant velocity, acceleration, or deceleration. And we can get uniform and non-uniform variations of these, but those are the basics of motion. Now, Newton's third law is actually pretty straightforward to recognise because there's always two bodies. If body A exerts a force on body B will exert an equal and opposite force to it. Now, you've probably heard this equal and opposite force cliche a bunch of times in movies, cartoons, whatever, but there'll be always two objects, but they're not always easy to recognise. So the force, if A and B are rolling towards each other and come into contact, the force will be equal, but in the opposite direction, which is what this little minus indicates here. So here's an example of Newton's first and second laws as applied to a skydiver, and this is also quite a common question in GCSE physics, or any of the combined courses as well. So, a little reminder here, if it's Newton's first law, it must be a constant velocity or stationary. Newton's second law, we must have acceleration or deceleration. Okay, so I've got a graph down the bottom here, and we're going to plot what happens to the skydiver's velocity as he falls. So the force, the minute the skydiver steps out the airplane, no longer in contact with the floor of the airplane, weight, which is equal to mg, will be causing him to fall. Now, unless the skydiver changes his mass or the gravitational field strength of the Earth, this force will stay the same constantly throughout the whole process. So that's going to result in an increase in vertical velocity, as in falling down speed, that is caused by the weight being larger than any other forces. In this case, it's the only force so far. So that is an acceleration, therefore it's following Newton's second law. Now, as the skydiver falls faster and faster, drag is going to increase because on the way down, there's going to be loads of air particles, billions and billions of air particles that the skydiver is going to hit into. As a result of that, that's going to cause an upwards force, drag or air resistance, and that's going to mean the resultant force, so in this case weight is still bigger than drag, so there is actually a resultant force. So they're not going to decelerate as such, but they won't accelerate as fast. So if you think about the gradient of this velocity time graph, this will be equal to acceleration, and you can see that as we move up, the acceleration, or the gradient, is getting smaller. So the rate of increase of speed is getting smaller. So after a fashion, they will reach a terminal velocity because the force of drag and the force of weight will be equal. So here we have a constant velocity. The forces are equal and opposite. So you could say this is an example in Newton's third law. But because they're moving at a constant velocity, we'll stick with Newton's first law. The resultant force is equal to 0 because weight is equal to drag. Now, skydiver opens the parachute, and you can probably guess what's going to happen to the forces. This big parachute is going to catch a whole lot of more air particles with its large surface area, and drag is going to massively increase. This is an example, therefore, of Newton's second law, because they will decelerate. You can see the velocity going down here. But as they start to decelerate, they'll be hitting less and less of these air particles. Therefore, drag will shrink back down again. They won't hit the air particles as often. They'll reach a new lower terminal velocity where once again weight will be equal to drag. So in this section here, we had drag was much bigger than weight. Remember, weight's not going to change, so they were decelerating to reach constant speed. Now, this is a word that's often missed out or forgotten in revising, and it's going to be a 1 marker at most in GCSE exams. What is inertia? And you can see what's happened here. Whoever was driving in here, it looks like they may have had a lucky escape, because when they hit the brakes, this mass of rock sitting in the back here was also traveling at the same speed of the truck. Now, friction on the bottom of the truck wasn't enough to slow it down, so this massive rock has tried to keep on going. And that kind of gives us our definition of inertia. Objects can be difficult to change their motion. So under GCSE, you need to be able to say that a tendency of an object to remain at rest or uniform motion. So basically, if you try and push someone next to you, they don't move very easily because of what's called their inertia. Now, last but not least, we have Newton's third law, and we've got our equal and opposite, and we've got our two bodies, body A and body B. And in order to give an example of this, we're going to use the classic 80s film Predator with Arnold Schwarzenegger. Now, here you can see Arnie going in and high-fiving his commanding officer, who I believe, if my 80s memory is good, is called Dylan. And Arnie's absolutely enormous. He goes in and they have a pretty epic high five, maybe the best high five of all time. Now, in a high five, even though Arnie may be stronger here, the force that they would experience would be exactly the same. When you give someone a high five, we've got, once again, what are two objects here, object A and object B, and it doesn't matter if one object hits harder or the other one hits harder if you're both moving. You'll both experience an opposite force, so it's kind of like punching a wall. The harder you punch the wall, the harder the wall is going to push back. So object A will exert an equal and opposite force to object B. So here's some examples of Newton's third law. It's all about identifying the two bodies. So let's start with the bird. So the two bodies here, we have object A, which is the bird, okay, and object B, which is the air. So the bird pushes down in the air pushes up on the bird, okay. With the rocket here, let's assume this is traveling at a constant velocity. We have the force of the rocket on the fuel, okay, and the force of the fuel on the rocket. So the fuel coming out the back is what pushes the rocket forward. In the example of the car here, there is friction from the wheel on the road, and there's friction from the road on the wheel. So it's an equal and opposite reaction. Sitting on a chair, this is a pretty straightforward one. We have weight versus the normal force, an equal and opposite reaction. Now that's a bit of an unusual one because normally you would have weight of the planet versus weight of you, or normal force of the planet versus normal of you, but it's okay to use this example. It's pretty accepted convention. With the boxer, that's a pretty obvious one. We have object A and we have, unfortunately, object B, but the force that the boxer here experiences will be exactly the same as the force as the boxer here experiences, but in the opposite direction. There's a couple of ways you can interpret the weightlifter here. We could have object A being the floor, object B being the weightlifter, or we could have object A being the dumbbell, or an object B being the person lifting it up and down. And here we have another similar example where we have the force that you push down on the springboard with is equal and opposite to the force that the springboard pushes back with. So, can you identify or can you remember Newton's 3 laws? The main thing to remember is one of the laws, there's acceleration or deceleration. One of the laws, there are 2 objects. Can you remember which one is which? Newton's first law, we have constant velocity. So that's either not moving or it's moving at a constant velocity, for example, 3 meters per second. Newton's second law, we've got acceleration, so an object is going to be getting faster or slower. And Newton's third law is where we have 2 bodies. So if you think of 2 things pushing apart, or a grenade suddenly explodes into 2 unlikely but maybe possible equally sized pieces, they will both push off in different directions. And this is kind of what leads us into momentum, which you cover in, if memory serves, P10. All right, I hope that helped.